Hi everyone, I'm Mintu and this video is about how there's more to dyes than meets the eye. First, let's take a look at these pictures. The first is a scale insect, the second is a predatory sea snail, and the last is the flowers of a longwood tree. So when you look at these pictures, what comes to your mind? Weird animals and a random tree, for sure, but dyes? Probably not. These are just some examples of animals and plants highly valued as sources of dyes in the past. The key feature that distinguishes man from the rest of the animal kingdom is culture. The first inklings of culture developed in the underground cave paintings of 15,000 BCE, created using a variety of dyes. To man, these caves were the only way to commune with the supernatural realm. And then later, at about 10,200 BCE, man's mastery of dyes became even more advanced, and man started dyeing textiles. Most dyes were extracted from common, locally accessible materials. For example, onion skins and turmeric gave yellow pigments, but they were faint, temporary, and used by the commoners. The brighter, more permanent colors needed special ingredients which were very expensive. An example is Tyrian purple, extracted from thousands of snails and could only be used by Roman politicians and the Roman emperor himself. For a long time, dyes could only be extracted from nature until 1856, when something amazing happened. William Henry Perkin was making quinine, a malarial drug, when he accidentally made Malvin A, a purple dye. As the first ever synthetic dye, Malvin sparked a craze among chemists to make more dyes in the lab, ranging from inulin, safranin, to fuchsin. And more importantly, this caused interest in organic chemistry to surge, and many chemical reactions were scaled up for the first time. Apart from their aesthetic uses, dyes are also crucial to science. For example, they're ubiquitously employed as pH indicators in titrations, used to determine the concentration of an acid or base accurately. Dyes are suitable because they give distinct colors depending on pH, allowing the endpoint to be easily visualized. An example is phenolphthalein, which is colorless in acidic solutions of pH 0 to 8.2, but magenta in alkaline solutions of pH 8.2 to 10. So what's so special about dyes that makes them colored? This was explained only in the 1930s using the molecular orbital theory. Electrons are placed in pairs into molecular orbitals, which describe the most likely positions that one can find electrons around the nucleus. No two orbitals are the same, and they rank from lowest energy to highest energy as shown. After all the electrons are grouped into their orbitals, the remaining high energy orbitals remain empty. To understand why dyes are colored, we just need to focus on the highest occupied molecular orbital, or the HOMO, and the lowest unoccupied molecular orbital, or the LUMO. Electrons in the ground state stable HOMO can be pushed up or excited to the higher energy excited state LUMO if they are provided with discrete energy packets, whose energy exactly matches the energy gap between the HOMO and the LUMO. So you might be wondering, where can we find these energy packets or photons? Well, the answer is light. The wavelength of visible light ranges from 400 nanometers to 700 nanometers. When white light shines on dye molecules, it contains photons with a wide range of wavelengths corresponding to various colors. But only those photons with wavelengths exactly matching the dye molecule's HOMO-LUMO energy gap get absorbed by the dye. In this case, only red light is absorbed. All the other photons are simply reflected into our eyes, and the color we see is complementary to the color absorbed. Since red is complementary to green, the color of this dye to us is green. By now, all of us might think, well, that's all there is to dyes. As the title suggests, no. In early 2000s, organic chemists discovered dyes' effectiveness as catalysts for light-driven reactions called photoredox catalysis. Chemists were interested in light-driven reactions because light is a green energy source compared to heating, and these reactions had new reactivity and selectivity. Dyes were attractive catalysts because they were readily available, cheap, and less environmentally detrimental compared to rare earth metal catalysts like iridium, which are toxic, scarce, and expensive. So how can dyes act as catalysts? Well, first, the dye absorbs suitable light to be excited to D star, as we saw earlier, And this D star can either accept an electron from reactant R, as shown in route A, or it can also donate an electron to reactant R, shown in route B. Let's focus on route B. By giving its excited electron to reactant R, R is reduced to a species called radical anion R because it has an extra electron and because it's negatively charged. At the same time, D star is oxidized to a species called D intermediate radical cation, which is more stable. The radical anion R is extremely reactive and it can react with another reactant S to form a new product, RS radical anion. This RS radical anion has a negative charge and it has to somehow give this away, and it does it to this D intermediate radical cation that we formed earlier, which then reduces it to the original dye D. At the same time, the neutral product RS is formed. This completes one catalytic cycle and D can continue to catalyze more reactions. To summarize, we have learned the importance of dyes in human culture since prehistoric times. Dyes are also a status symbol throughout history and revolutionized the chemical industry in the 1850s with the discovery of synthetic dyes, showing that, well, chemistry can make money. Even today, dyes play crucial roles in science, as pH indicators for example. And finally, at the start of the 21st century, chemists made yet another breakthrough with dyes, photoredox catalysis. Even now, I still wonder, what other surprises do dyes have for us? Currently, numerous research groups, including mine, are working on photoredox catalysis, with new breakthroughs emerging every year. Only time will tell as to the limits of these dyes in organic synthesis. Thanks for listening to my short video, and remember, there's truly more to dyes than meets the eye.